So, good evening, students. So, in the previous class, we were dealing with the approximate method. Especially, I think we covered the example for the assume mode method. And in assume mode method, we saw that uh, the function in the form of admissible function, we can able to choose for the response, and that is having less requirement because only geometrical boundary condition need to be satisfied. Also, I gave in the example I gave two types. One, I chose the comparison function, and then another admissible function. We found that when we take comparison function, then the results are better. But often it's not possible sometimes to choose the comparison function. Today we will see that which requires the comparison functions to be chosen in the series when we are generating the response. So here in the Galerkin method, the requirement is more, and through example, we'll see how this method works. And if we are choosing in previous method, assume mode method, comparison function, and anyway in the Galerkin method, we need to choose comparison function, then we'll find that the solution accuracy will be same. But if we use admissible function in the assume mode method, then accuracy will decrease. And also we have seen that if we take more and more number of terms, the lower natural frequency will be having more accuracy. They will be converging toward the actual or the closed form values. So I'll share the slide for the today's lecture. Yeah. Okay. So I already described the method in the last class. What we did, we took the basically eigenvalue problem, and then we assumed the solution in the form of comparison function series. We substituted in the equation of motion, and we set key because the solution is approximate. There will be some residue left out, and then we minimize the residue over the domain, and the parameters which the constant which were there in the series form of the solution, they gave us some kind of homogeneous simultaneous equations, and that gave us the eigenvalue problem, equivalent eigenvalue problem of the continuous system in the form of discrete system. So the same problem I am taking, which I solve using the assume mode method, in which the mass distribution and the elastic distribution is given to us. But now we are using the Galerkin method, and we again am considering the transverse vibration. And here anyway we need to choose the comparison function. First we'll choose single comparison function in the series, then we'll take two, and we'll see that how the result improves with the more number of terms in the series. So this is the given distribution, and then for bending a beam, we know this is the L operator and M operator, because in the Galerkin method we need these operators. Okay, so coming to the boundary condition, we have 4 boundary condition, 2 geometrical boundary condition at the at x is equal to 0 and L, displacements are 0 because simply supported beam. And then the bending moment is 0 at both ends. So these are the 4 boundary conditions we need to satisfy. And the comparison function, as we chose for the previous method also, is here. So we already checked this, that it satisfies the all 4 boundary conditions. So there is nothing new in this function. The same thing is there. Now we need to calculate the coefficients using the Galerkin method. The procedure of the calculation of the coefficients, stiffness and mass is slightly different here. You can see stress coefficient L operator. So here L operator we already know for the beam case. So it will be like this. So here the differentiation of the assumed solution is of the 4th order, which was 2 in the case of assumed mode method, because we started with the energy form. So that's why here we insist that the U should contain the comparison function, not the assumed mode method, not the admissible function. So for calculation of this, we need to obtain this L operated on the assumed solution. So this is the U1, L U1 we are operating. U1 we have chosen earlier in the previous slide. This is the comparison function. So we need to differentiate this, and then we got from the first differentiation this. Then because variation of the EI is there, so that also we need to substitute in terms of X. Then here again, after multiplication, we need to do the differentiation. So if we do this, we finally will get LU1 like this. Now take R is equal and J is equal to U over the domain. We'll substitute. Let us this is the once we substitute and integrate, we can 0 to L, and then K11 will be something like this. Similarly, MRJ and MJR can be calculated using this, which in the last class we derived through the Galerkin method. And because M operator is just a function M, so we'll be having this. So if we want to obtain M11, so U1 MX U1, so basically U1 square will be there. So this is the U1 square, and MX, because variation of the mass of the beam is there, and that is given by this. So we need to square it, multiply it, and then integrate over domain 0 to L. So we'll get M11 like this. So here you can see there is slight difference in the differentiation in the L operator. M remain the same because M is having no differentiation. M will be same as the assumed mode method, but only K11 is changing here. Now we got K11 and M11. Only one function we have chosen. So first natural frequency will be just simply the ratio of this square root. So we'll get the natural frequency like this. And the eigenfunction will be, because only one function we chose, comparison function. So multiplied by some constant will be the eigenfunction, because eigenfunction is always relative. And for any value of x, we can able to find out what will be the displacement in between the beam. So that will be nothing but the mode shape. So at the end, we'll plot this also. But now let us take the second comparison function. So first, anyway, we have chosen earlier. This also we are taking. So we have now two terms in the solution, u1 and u2. And this also we have checked earlier satisfies all the four boundary conditions, natural as well as the geometrical boundary condition. So now calculation of the coefficients. So mass coefficient now M11 that remains same because u1 function is same, is the u1 function, which is fourth degree polynomial. So this M1 coefficient I think will remain same. There will not be any change. M12 will change because u1 mx u2. So as per subscript 1 to u1 u2 will change. But if you compare with the assume mode method, because m is just function, so as compared to the assume mode method, this m12 also will be same and m22 also will be same because they are this we have chosen the same function and the m is having no differentiation here. So we got the mass matrix. Now the stiffness matrix. So stiffness matrix requires the L operator to be we need to perform on the U2. So U2 we have chosen fifth degree polynomial. So if we operate this first, this differentiation, then this, and EI is also there. So this is the first when we took two times differentiation of this, then EI is given by this. And now we need to differentiate after multiplication of this twice. So we'll get L operated on U2 as this. So now K12 will be integration U1 LU2. LU2 we have already obtained here. So this we can substitute. This is L operated on U2 and this is the U1. So then if you again multiply and integrate, you'll get K12 and 2-1 also will be same because this is symmetric. For K22, both U2 and L operated on U2 will be there. So basically this is U2 and this is L operated on U2. So if we multiply and integrate, we'll get this. So we got the both mass matrix and stiffness matrix. I think the mass matrix remain the same as the assume mode method because we chose the comparison function, but we chose their admissible function also. So that case, this will not be same, but stiffness matrix is different here. I hope so. Or if we take the function, maybe we can check it. I think they should be different here because we have differentiated. Maybe the power of this may be different. So now this we could able to convert into 2 degree of freedom equivalent system of the continuous system of the beam. So this is very important to understand that we are discretizing a continuous beam having varying mass property and stiffness property to 2 degree of freedom system, equivalent to degree of freedom system, and then we can able to obtain the eigenvalue problem for that, and we can get the first natural frequency and corresponding mode shape, or sorry, this is eigenvector. Eigenvalue will give the natural frequency. Eigenvector is this. Eigenvector can be used in the assumed solution. So this is first comparison function. This is second comparison function. A1 and A2 are the constant, which we are getting from the eigenvalue problem. So if we substitute this is the corresponding eigenfunction for the first mode. Similarly, for the second mode, second natural frequency is this, and corresponding eigenvector is this. And if we substitute that in the assumed solution A1 and A2, we'll get the second eigenfunction. And this, if we plot, this is the first mode. We know the half sine wave, and this the second mode, full sine wave. Here, we have taken only two terms. If we want more accuracy or more number of natural frequency, then we need to take 3 term or 4 terms. So we need to choose of 3 comparison function or the 4 comparison function. Then these matrices will be 3 by 3 size or 4 by 4 size, and correspondingly the natural frequency will be 3 or 4. In general, n. If we are taking n terms here, we'll get n by n size of the mass matrix and stiffness matrix, and that will be giving us n natural frequency and corresponding eigenvector. They can be used here to obtain the eigenfunction for the corresponding natural frequencies. But for illustration purpose here, only 2 natural frequency are demonstrated, but it can be taken more also. This is the same code. Only thing is whatever the changes in the differentiation of the comparison function is there, that has been incorporated, but overall the calculation of the stiffness coefficient, mass coefficient, they are same. So this can be used, and these are the output from this particular code. Okay, so now especially when we are talking about comparison function, in the previous example, I took up the simply supported beam. Geometry was complex. The elastic property of the previous problem was complex, but the boundary conditions were simple. That was simply supported beam. Now in this, I just want to illustrate how if the boundary condition contain more complex things like spring is there or disk is there, then how we can able to tackle that, and how we can able to obtain comparison function for that or admissible function for that. Because so this problem is that the taper beam is there, and then one spring is there at the free end. We are considering now the axial vibration. So this should be noted that now we are not considering the bending vibration, we are considering the axial vibration. And at free end, we have the axial force as that is equal to the elastic force coming from the spring. So this is the natural boundary condition. This end, we have one geometrical boundary condition that the displacement is 0 at x is equal to 0. Because this is axial vibration, only 2 boundary conditions, one here and one here will be there. Here geometrical boundary condition is there. Here this natural boundary condition is there. If we want to choose the admissible function for this, then like if we want to use assume mode method, then this is relatively simpler since only geometrical boundary condition need to be satisfied. But if you want to choose the comparison function, then we need to take care of this boundary condition that so the comparison function should satisfy also this boundary condition. So here, what is the thing we do generally? So let us say if this beam is not varying continuous varying, is a uniform beam, and this spring is also not there. So there is nothing but a cantilever beam. If uniform cantilever beam is there, already for axial vibration we have obtained the eigenfunction in closed form using the eigenvalue problem solution in chapter 5, and this is the eigenfunction for that, where for all odd value of this we have this term 0. So only the odd values of this, because if we put R1, 2, 3, this becomes odd, and that is the eigenfunction we obtain for the cantilever uniform beam for the axial vibration. Now, when we are talking about admissible function, which is required in the assume mode method, this itself can be taken for non-uniform beam with spring, because it need to satisfy only the geometrical boundary condition. So at x is equal to 0, in anyway this becomes 0. So this is this satisfying our requirement, that geometrical boundary condition at u is 0 at x is equal to 0. But if you want to use, use, let us say, Galerkin method, in which we need the comparison function, then this cannot be used, because this boundary condition, it will not satisfy. So we need to see how we can able to satisfy this. So for that, we need to do something, change in this. So what we'll do, we are assuming that the comparison function is some constant sign. Instead of this pi and those things, nice number, we are writing s. S is some number, that can be a real number, s x by l. And now our aim is to obtain s, which will satisfy both the boundary conditions, this geometrical boundary condition and the natural boundary condition. So that is the aim. So S has to be found out so that we can able to satisfy the all two boundary conditions of the problem. So now, because this function is sine, so anyway this is satisfying the geometrical boundary condition that x is equal to 0, u is 0. So if you put x is equal to 0, this becomes 0. So geometrical boundary condition, there is no problem for this function. Now for the natural boundary condition, at x is equal to 0, we have this condition, this condition. Now we'll substitute the assumed solution in this. So we have the derivative of the u, so that will give us s by l cos this term, and minus ku, u if we substitute, and c is common, so that will get cancelled. So we got this. Now we can substitute l. So wherever x is there, we can put l. Then if we simplify, we'll get a transcendental equation like this, in which if we know the distribution of the beam, varying beam, geometry, length of the beam, and stiffness of the spring here, then we can able to solve for S. And once we solve for this, for S, because this is a tangential equation, we'll get infinite solutions of S. And here, S, this is not a frequency equation, we should remember here, because we already satisfied the boundary condition to get this. Earlier we used to go for the eigenvalue problem, but here just we are satisfied the assumed comparison function to the boundary condition to get this. So S, which where we got it, if we substitute here, we'll get, as I told, we'll get infinite number of such solutions. So we'll get infinite number of such comparison functions. So for S1, we'll be having one comparison function. S2 will be having another comparison function. S3 will be having another comparison function, because this S1, S2, S3 have been obtained after satisfaction of the natural boundary condition. So all those S value which we have got from this equation will satisfy the natural boundary condition. That means for all those value, this will be the comparison function for us. So this is the thing now. Si will be having infinite number of solutions from this, and for that we need to know the geometry and length and stiffness of that we can able to obtain using any numerical method. So this is the comparison function for the this particular problem, in which we have chosen the spring here. Always the comparison function finding is not easy. Now here itself we can see we need to satisfy the natural boundary condition, and then we got this equation, we need to solve this, then only we got another equation. So here you can see that SI is some number, but not so nice number as this. Here we'll be getting pi by 2, 3 pi by 2, 5 by 2 like that. But here we may get some fraction values also. And so finding this is slightly tedious. And that too, we have taken the axial vibration. Now I'll just demonstrate just to feel how complex it can become, finding the comparison function if we have the bending of beam case. Just for feel of the problem, I want to illustrate that. So for same similar beam is there. The only thing is the spring is in the vertical direction because is now vibrating vertically because there's a transverse vibration. Boundary conditions will not change because now we'll be having two boundary conditions here. Displacement is zero, slope is zero, and here we'll be having shear force equal to the spring force, and bending moment is zero. So if we have some kind of a torsional spring here, then that can be incorporated here. But no, that is not there. Only linear spring is there. So the shear force is taking that particular spring constant. Now, how we can able to get the comparison function for this is, so the idea is we already have some information from the uniform cantilever beam as we started for the case of the axial vibration case. So here also we are taking the uniform cantilever beam, and we have the eigenfunction in the form of sine, cosine, hyperbolic sine, and hyperbolic cos functions. Here S parameter is there, which we need to find out so that they satisfy all the boundary condition of the problem. So as we did for the axial rod case, previous case, here the complexity is more. We have associated constants also, and four boundary conditions are there. And they require the first derivative, second derivative, and second and third derivative of the W. So that have been done here. We have taken the derivative of this first, second, third. This similar exercise we did it for the in chapter 5 when we were dealing with the continuous system using closed form solution. But here we are doing the approximate method. Just we are trying to find out the comparison function. So here we got this. Now we need to satisfy the boundary conditions, these. So first boundary condition gives this relationship. If you remember, these similar expressions which we had earlier. The first one, second one, just we need to substitute x is equal to 0. So some terms will be 0 and some will be will be equal to 1. So from first to boundary condition, geometrical boundary condition, we are getting this C2 is equal to minus C4, C3 is equal to minus C1. Now from the third boundary condition, bending moment, that is the second derivative. The second derivative, if you put x is equal to L, because that is at the x is equal to L. So wherever L, if you put in the previous thing, so we'll left with the S only here. So that is sine S, cos S, cos H. So these are the thing for the case of the bending moment. Also, we replace C3 with C1 and C4, C4 with C2. Okay, and then this equation is only in terms of C1 and C2. So we can write C2 is equal to C1 and this. Now left to the third boundary condition, that is the shear force. So shear force is this one. So all the terms in the other three boundary conditions were 0, but now stiffness is coming. So instead of putting 0 here, Now we are putting minus k WL. And we have put x is equal to L, so corresponding terms becomes like this. Now we can able to rearrange this. Also, if you see WL, what is WL? We have already expression for W. So if you put L here, we'll get the WL. So this is the WL expression. So this also we can substitute here in the left side of this. And once we substitute, this equation becomes like this, and this can be rearranged. C1 can be collected in one place, C2 can be collected in other place. And then this equation again can be simplified, because here aim is to eliminate the C2 also from here using this. So that you can see if we substitute C2 here, the whole expression will be in terms of C1, and that will be common also. So C1 will get out of all the terms. So these are the all steps in which we are trying to do the. So you can see C1 is common. C1 cannot be 0, so this term will be 0, and that yeah, here C1 is common, so C1 cannot be 0, so this whole term will be 0. So this is the equation. Again, this is not frequency equation, this is the equation or the condition that we need to find out S, which will make the assumed solution, this one, a comparison function. So we need to solve this for S, where the K, L, all those parameters of the beam will be involved. And this will give us the S value, and that can be substituted in the assumed solution to get the comparison function. So, but this becomes very complex. So that's why the admissible function itself will be good enough for this, which we can take, and even the sine function can be chosen as admissible function, and we can solve the problem. Only thing is here maybe we can take more number of sine terms, so that we can have more degree of freedom we are discretizing, so that we can get the more accurate lower natural frequencies. So this is just I wanted to show the complexity of the comparison function. So that was the idea. So this is the last method of the approximate method, which will be covering. There are so many other methods, but this is the last one. Just wait a minute. So this is the collocation method. This method is having a lot of flexibility, in which we assume some kind of assume solution. Here also we take combination of some function. So just to distinguish from the previous two method, we are writing that functions as V. This V can be comparison function or admissible function or other functions which we am describing below, and associated constant we need to multiply. So the form of the solution will be the series form multiplied by the constant. And depending upon the nature of the V, the function which we are choosing, the problem can be three types. Boundary method, whatever the function which we are choosing, satisfy only the differential equation, but not the boundary conditions of the problem. So a function need not satisfy the boundary condition, only the differential equation should satisfy. So that is the boundary method. Interior method, function satisfy on the boundary conditions, but not the differential equation. So this is the other way around. So then next method in which function satisfies neither the differential equation nor all the boundary conditions. So here a lot of flexibility is there because based on the complexity of the problem, we can lower the requirement of the function. It need not be comparison function. It need not be admissible function. Here you can see that even we are not talking about it should be differentiable up to P or 2P or should satisfy the geometrical boundary condition or natural. So we need some solution. That is the aim. And depending upon the complexity, because if you're not able to solve the problem, better we use some approximation and then try to get. But the method is relatively easy, but we'll see the complexity in the solution of the eigenvalue problem here. Because in this particular problem, we'll see that the mass matrix and stiffness matrix of the discretized system which we will get will be asymmetric. That will not be symmetric, and is having associated interpretation of the eigenvalue and eigenvector, and so that complexity is there. But let us see the method. So here, what we do, we choose the function depending upon the three methods I described earlier, and a set of locations on the structure we choose. So that is called stations. So set of locations we choose. So like if there is a simply supported beam, so in between we'll take 1 or 2 or 3 points, either at the mid span or at 1/3 location or something like that. So these are called stations. The stations can be on the boundary or within the domain of the domain. That means within the beam or at the boundary of the beam. And here we again this coefficient which we multiply in the series form determined by insisting that the selected function satisfy either the boundary condition or the differential equation, depending upon which method, boundary or interior or mixed problem we are chosen. So here I am illustrating the interior method only. So here we know that if you just to recall, for continuous system we had the eigenvalue problem like this: L operator on W, lambda is the eigenvalue, and M operator W. Here we assume the solution in the form of series like this. So here, depending upon the method we choose, here we'll be choosing V. But once we have chosen the approximate thing, then we substitute here. So once we substitute, we get error, like a Galerkin method, we get error. So up to this, it looks similar to the Galerkin method, but from here it deviates. How it deviates? In Galerkin method, what we do, we minimize this error over the domain and then integrate and equate to 0. But here we are not integrating. What we are doing it here, we are saying that this error we are trying to minimize, or we are saying is vanishing at the chosen stations. So we are chosen in between some stations. We are saying this error vanishes at those stations only, and from there we are getting the conditions. So now you can see that in the previous thing, this is the error. This was the S. Now I put the station location here, SR. SR. Okay. Now here you can see that uj is function of x, and x we have written as SR. This is a fixed location on the beam, maybe the mid span or 1/3 position, something like that. So this is the known position which this user can choose. Now, once we have this, we can substitute this series form of the thing here and here. And then, because this is a differential operator L and M, and the summation can be interchanged. So here that has been done. Summation we are keeping outside, L operator inside. So once we substitute this here, we are changing the L operator and summation, and we are keeping the summation outside here also. And that we are saying key at those stations where we have chosen. So here, depending upon the number of terms, that many number of stations we are choosing, and this we can able to. We are saying that this error becomes 0 at those stations. So as simple as that. So we are not integrating over the domain. Just we are saying this error becomes 0 at the chosen stations. So chosen stations can be any number depending upon the accuracy required. Now we are representing this term within the, that is underlined term, as KRJ, and this term which is underlined is called MRJ. These are the stiffness coefficient and mass coefficients. So here this is representing that, so this instead of W, this VJ is there, and SR is the location of the station on the beam or any structure. And once we use this here, if we write KRJ and MRJ, this can be written in this form, which is familiar to us. And this again, these are simultaneous equations, can be written in matrix form like this. So here only problem is K and M matrices are not symmetric. That you will find that the K and M will not be symmetric. So solution procedure for asymmetric matrices are different, but if you're using some software, then directly it gives the natural frequencies. The mode shape interpretation is more cumbersome, so I'll not describe that. So I'll take up the same example for illustration of this particular method. So here we are using the same beam, same variation, collocation interior method. We are using it for transverse vibration. So here the boundary conditions we know. So for comparison purpose, I'm choosing the same function as I chosen earlier. Basically, this is a comparison function just for illustration, but we can choose any other function also here. So maybe I'll advise you can choose some other arbitrary function and try to see how the result changes. Just I wanted to check this method for the same function, how it gives the result. So that's why I've chosen the same function. So if we know the procedure of the calculating the K stiffness. So stiffness requires the L operator on V1. So V1 is, we have chosen comparison function. L operator for the bending up beam is this. So if we operate this function is up to this, there is same as we have done in the Galerkin method. But here for obtaining the stiffness coefficient, we are not integrating, we are choosing one station. So let us say we are choosing as small as at mid span of the beam. So S1 is L by 2. So here K11 is L operated on this, but wherever X is there, we need to substitute L by 2. So as simple as that. So if we put X is equal to L by 2 at wherever the X location is there, we'll get the sum stiffness. Similarly, the mass, the M operator is anyway function is there. So I think M also should have the distribution here, because we have the distribution. This should be Mx, and this is the V1. So this is MX. So distribution of the MX we know is given in the problem that we need to substitute. Then we'll get this distribution, this mass coefficient. So now you can see here S1 we are putting X is equal to L by 2. So instead of the previous integration, we are just substituting the location of the station which we have chosen. The choice of the station is also we can decide arbitrary. And then once we got the K11, M11, we can get this the stiffness or the natural frequency like this. So if you remember, we got something like 9 point something, and for the Galerkin method, here we are getting 11.5 something for the first natural frequency. So relatively some value we are getting here. It's not very good, but at least some feasible value we are getting here. Now I'll take the second comparison function also, two terms in the assumed solution. So this is the same function. The procedure of calculation of this is now, because there are two terms, so we are taking two stations. S1 is L by 3 and S2 is 2/3 of the span. So K11 is now V1 S1. Now you can see that S1 is different. Previous S1 was L by 2, but when we took two terms, we have taken different stations. So calculation of the K11 is different here as compared to the previous, because now X is L by 3, earlier it was L by 2. K12 will be V1 function we'll be using. In that, the location will be putting S2. S2 is 2L by 3. So that is the difference. So when we are seeing K12, the comparison, the function is V1, but location is second one. So K12. Similarly, K22, if we want, that is there in the next slide. Yeah, here. So for K22, we need the first we need to take the L operator. So this is the L operator. K22 is V2 and location is also 2. So that is 2 by 3. 2 L by 3. So this is the K22. Here, as I mentioned, this is K21 and K12 will not be the same. So we need to calculate the K21 also. So L operated on V2, but location is S1, which is L by 3. So K21 is this. So here we need to calculate both K12 and K21 because they are not symmetric. So on the same line, we will be having for mass coefficient. When M11 is there, V1 S1, M12, V1 and S2, and M21 again, it will be 2 and 1, and that will not be same as the M12. So this is the steps for the mass stiffness and the mass coefficient. You can see now they are not symmetric, and this gives difficulty, especially in the eigenvalue problem. This has been solved using MATLAB, and we got first natural frequency. Now you can see earlier when we took only single function, we got 11 something, but actual value is 9.8 using Galerkin method. When we took two terms, then it is coming 10.9. So it's coming closer to this, but still away from that. So this second natural frequency is relatively closer to this. So using this method, because in this the integrations are not involved, just we need to substitute the location of the station into the functions and then simplify. So that's why it is relatively easy in calculation of the mass and stiffness coefficient, but eigenvalue problem is more difficult here. Anyway, so this is the collocation method or bending of beam case. This is the code for the same thing, in which now differentiations are not, integrations are not involved, just substitutions are involved. So, and this has been shown for only one K11 M11. For other K12 other things, this can be extended. Okay, so if you have any questions on this, then I'll attend that question. Then I'll summarize this section after this. If you have any question, quickly you can ask. Okay, so there's no question. So I'll summarize this particular section, because several methods are there and they looks very similar to each other. So that's why I try to summarize. Hello, any question? Okay. So I'm trying to summarize this within 2-3 minutes. So we started with the Rayleigh's quotient for discrete system. That was very simple. Just we need to choose the U, and then uh, based on the knowledge of the K and M, we can able to some. Let me mute all of them. Okay. So this is for the continuous system or discrete system, first one. This is we already know from very beginning. This was simple. Then Rayleigh's energy method for axial rod case. So Rayleigh's quotient. This is energy method for the axial rod case. So in which I think we started with the potential energy and that thing. And here energy method. Okay. So here we need to use comparison function because boundary conditions was not involved in this, so we need to use comparison function. Then Rayleigh energy method, the same method, but with the banding case, because in banding case we have the order of differentiation is different. So just I wanted to summarize. In here A is there, area is there, here I is there for banding case, and here differentiation is twice, but here still we use the comparison function for the Rayleigh's energy method. Then the Rayleigh-Ritz method. In the previous two methods, we get the first natural frequency. Rayleigh-Ritz method gives n natural frequency depending upon number of terms we use in the assumed solution, and the stiffness coefficient for simple beam case we got something like that, in which the L operator and M operators were there. So here anyway we need to use comparison function. Then the Rayleigh-Ritz method, when we re-examine the boundary condition, and this is for the case when we had the cantilever beam with a spring at free end. Then the boundary condition was included in the energy, and then we could able to choose the admissible function in the Rayleigh-Ritz method when we incorporated the boundary conditions, natural boundary condition in the energy. So, and in this case, we got the stiffness coefficient something like this. So additional, this is due to the spring which we had at the free end. If disk is there, then additional terms will come here. Otherwise, it will not be. So this is the Rayleigh-Ritz method with re-examination of the boundary condition with the spring. Then the same thing for the bending of beam case without spring and that kind of thing. Rayleigh-Ritz method, and here only thing is here double derivative is there in the K. In the previous case, single derivative is there when we are talking about axial vibration. For case of bending, we have double derivative of the comparison function. And then the assume mode method we had, which is similar to the Lagrange's equation, in which we, Rayleigh-Ritz method, similar to the Rayleigh-Ritz method. And in this, exactly same. So I'm not repeating here those expressions, especially when we re-examine the boundary condition in which the requirement of the admissible function was there. Then the Galerkin method, we had this form of the stiffness and mass, and here we need to choose comparison function. Then last one was the collocation method, in which the K is not involving any integration, which was there in the earlier methods. Just the differentiation and then the substitution of the chosen stations that gives us the stiffness and mass coding. So this gives the overview of the various methods because they looks very similar with some little difference, and because we have the axial dot case and bending, there the L operator, M operators are different, so a lot of confusion take place. So this will help you in, I think, understanding the all methods in 1-2 slides. So with this, I'm concluding now. So if you have any questions, otherwise, tomorrow I will start a new chapter. That is, now till now we have been bothered about the finding the natural frequency and the mode shape, except in the very first chapter we took up some response due to the step function or that kind of thing. So again, we'll go back to the response of the system because of the force. So maybe 3, 4, 5 lectures will be on that. Okay, if there are forces in the system, then how we can able to get the system response. But whatever we have studied from for the continuous system or discrete system, the natural modes, those things will be useful there, because when we are trying to solve the the force vibration problem, we need to first discretize the system to n degree of freedom system if it is a continuous system, because the continuous system as it is in partial differential equation is difficult to solve. So first step will be to discretize by the method we discussed. Then we need to see the forces associated with that. That also we need. The procedure of the forced vibration will start. So anyway, whatever we have studied will be required to start this forced vibration. So often is quite long. If you start the eigenvalue problem, then you then solution of that, and then you go for the forced vibration. So here most of the time directly I will give the eigenvalue solutions, and then from that point I will start the solutions of this. So with this, I am closing because I cannot see any questions. So anyway, on 16th, I think we have planned the one quiz based on whatever I covered till now on the approximate method. So you have some time, 1 week, and you can attempt the assignments. Some of you are attempting and getting good feedback from them. And I think today's lecture also I covered some of the confusions which students had. So I clarified in more detail. So I encourage you to write email with whatever the steps you are attempted and where you're facing the difficulty, so that I can understand where is the confusion, and that I can clarify in the lecture also then. Okay, then I'm stopping the video now.